Sikorsky Ilya Muromets. Imagine a Russian skylord from the early 20th century. Built in 1913, the Sikorsky Ilya Muromets was among the first multi-engine bombers ever produced, a true pioneer. Its wooden frame and fabric wings stretched wide as ambitions, carrying passengers or bombs depending on its mission. But with innovation came fragility. Early aviation meant unpredictable weather, materials warping under moisture, engines prone to failure, and little in the way of modern navigation or safety redundancy. Yet it taught critical lessons about structural integrity, engine placement, and balancing risk with reward. For any aircraft ambition today, the legacy of the Ilya Muromets whispers a truth. Pioneering larger always means pioneering danger, so test everything. Overbuild key structures, plan for failure. Bell Boeing V-22 Osprey. Next up, the Bell Boeing V-22 Osprey, tilt-rotor aircraft that can take off like a helicopter and cruise like a plane. Hybrid brilliance, engines that tip, rotors that swivel, making it supremely versatile. But this versatility comes with enormous technical complexity. Rotors that must transition from vertical to horizontal flight, control systems that must handle changes in airflow, and risk of vortex ring states or atmospheric conditions messing with stability. There have been accidents. Pilots must train intensively. Yet for special missions, search and rescue, military insertion, amphibious ops, the Osprey's strengths are unmatched. If you ever fly or design one, redundancy in hydraulics, rigorous maintenance, and predictable training cycles aren't optional. They're life insurance. Boeing 747. When most people say jumbo jet, they mean the Boeing 747, a four-engine titan that redefined long-distance travel, connecting continents. Its humpbacked upper deck became iconic. Capacity soared, distances shrank. But with size came rising wingspans, enormous fuel loads, gargantuan wings to maintain, and demands on airports to build runways, taxiways, and gates to match. Also, efficiency challenges, fuel consumption, noise regulations, emissions scrutiny. Yes, boarding 40 rows in the back can feel like entering a small city. For airlines operating 747s, cost per flight is massive. Scheduling must consider long service intervals. Weight distribution and payload limits are serious science. To fly or build anything in its class, you must anticipate regulation shifts, fuel price volatility, and life cycle maintenance that could outlast simpler designs. Zeppelin NT. Floating between aircraft and lighter-than-air wonder, the Zeppelin NT revives the spirit of dirigibles with modern safety. Helium lift, sleek control, gentle cruising. It's quiet, majestic, perfect for sightseeing. Yet the trade-offs are subtle and deep. Speed is low, weather sensitivity high, lift constrained by envelope size and gas purity, and operating costs relative to speed are often less appealing. Imagine being delayed because wind gusts make you sway like a tethered balloon. Controversies over safety come back with anything lighter than air, fire risk, gas leaks, and regulations for airspace usage can complicate routes. If you're designing or using an NT-class craft, think about worst-case weather paths, rigorous helium maintenance, and public perception, because anything that floats is under scrutiny. Aeroscraft. The Aeroscraft project aims at hybrid airship technology, blending buoyant lift with aerodynamic lift to carry heavy loads without runways. It's futuristic freight, huge payloads, minimal infrastructure. Yet that promise struggles with complexity, managing static lift versus dynamic lift, controlling buoyancy as cargo is loaded or offloaded, dealing with crosswinds and mooring, and engineering materials that are light yet strong enough for massive pressure differentials. Yes, a small tear or seam flaw could become a big problem. Also, funding over decades has seen delays and shifting design goals. If you're on a team building something like Aeroscraft, designed for modularity, simulate environmental stresses, and build robust safety margins, even for what seems redundant. Boeing Phantom Eye. Enter the Boeing Phantom Eye, an unmanned, high-altitude, long-endurance aircraft designed to loiter in the stratosphere for surveillance, communications, or scientific missions. It's thin, Lightweight, high wing aspect ratio. Sipping fuel, but doing work up where most aircraft can't go. But the risks? Extreme cold, high altitude thin air, material fatigue from thermal cycling, controlling lightweight wings under turbulence, and loss of power margin. Also, unmanned doesn't mean risk-free. Ground control, communication latencies, RPAS regulations all matter. Imagine being thousands of feet up and waiting for signal to come back after a solar flare. For projects like Phantom Eye, reliability, remote redundancy, avionics hardened for extremes, and thorough flight testing are non-negotiable. Lockheed Martin, C-130, Hercules. A workhorse legend, the Lockheed Martin C-130. Hercules, rugged, versatile, able to land on short, rough runways, fly in low visibility, haul troops, supplies, vehicles. It's built to take abuse. But size brings logistical strain. Fuel consumption high, maintenance demanding, transport of large cargo burdens airports and ground crews, and older airframes may suffer from metal fatigue or parts obsolescence. And yes, partnering with remote airstrips means improvising when spare parts aren't in stock. For any operator of large transports, having predictive maintenance diagnostics, spare supply stockpiles, and flexibility to adapt to field conditions. S-64 Skycrane. The S-64 Skycrane, a helicopter built to lift other aircraft or heavy loads. Massive rotor, skeletal frame, pure utility. It doesn't carry many passengers, but lifts huge things. Yet lifting heavy loads under helicopter rotors means risk. Rotor downwash, lifting stability, strong torque, precise pilot control, and weather dependency. Plus, logistics of transporting the Skycrane itself or fuel to remote sites matters. Picture hovering over a mountain, wind swirling, carrying hundreds of tons beneath you. If using something like Skycrane, rigorous crew training, strict load assessment, constant maintenance on rotors and hydraulics, and always plan for emergency load jettisoning. Boeing C-17. Globemaster 3. The Boeing C-17. Globemaster 3 is another giant strategic transport. Get heavy equipment anywhere in the world with speed, precision, from austere bases. Huge wings, big engines, massive cargo bay. But it comes with steep operational and maintenance costs, crew training demands, rigorous inspection needs, and environmental constraints. It burns a lot of jet fuel, runs on many systems that must be redundant. Avionics must be up to worldwide standards. In some regions, infrastructure can't accommodate its size. For anyone managing one, plan ahead for spare parts globally, perform structural inspections frequently, and always have fallback landing sites. Concorde. Last, the Concorde. Slender, sleek, supersonic. Concorde was about speed, prestige, pushing air travel limits. But supersonic flight introduces huge risks and costs. Sonic booms, aerodynamic heating, extreme maintenance, fuel inefficiency, especially when oil prices rise, environmental critique over emissions. Also, noise restrictions, limited routes, expensive tickets made commercial viability narrow. Yes, breaking the sound barrier sounded dreamy, until every airport nearby banned you. For any future supersonic project, anticipate regulatory restrictions, ensure materials engineered for high temperatures and metal fatigue, design for efficient economics, and brace for public and environmental resistance. If you enjoyed this journey through sky giants like this video, subscribe for more and share so more people can marvel with us. Drop a comment. Which aircraft blew your mind the most? Size, speed, history? Thanks for flying with me today. Thanks for flying with